All right, we're getting started from one of my least favorite units to one of my favorite units. We're going to be talking about trigonometry this unit. We're going to, since this is geometry, it's fun. It's kind of fun to cover this in geometry because we get to kind of hit it in a foundational way. We kind of build up the foundations for trigonometry, and then in pre-cal or in a dedicated trigonometry course or whatever, we can kind of build from there and use some of these foundations to do some really, really awesome things. Trigonometry is one of the most practical maths that exists. You can use it for all kinds of things in real life. So let's dive in. This is going to be a really notes heavy lesson. This particular one, we're going to hit a lot of concepts and kind of get it's some underlying ideas, some theorems. I know I said no more proofs, and I was not lying. We're not going to do any more proofs this class, but we are going to learn more theorems, right? Because theorems are those building blocks that let us build tools that are useful. Actually, theorems really are tools that have been built that are useful for physicists and for engineers. From this point on in this course, a lot of this class is kind of prep for physics class and prep for algebra 2. We're going to hit a couple of things that we're going to hit really heavy next year in algebra 2, and we're going to kind of start to learn. Some of you may have started to learn them in algebra 1. But anyway, the first thing is we're going to kind of talk about a geometric mean a couple of different ways. The first way is when the means of a proportion are the same number. So you can see this x. So when the means are the same, that number is called the geometric mean. So if of the extreme. So it's just kind of the parts of a proportion. So if it's the same number right here, right, is if two numbers are proportional to the same number, then that same number is the geometric mean. So let's look at it another way. So geometric mean is also the positive square root of the product of two numbers. Okay, so the geometric mean of two positive numbers a and b is the number x, such that this is similar to what we just saw, right? We've got the extremes and the means, right? So if we were to like solve this proportion, we would cross multiply. X times x is x squared. A times b is a times b, right? And so then to get the x by itself, we take the square root of both sides. Now, we've learned before, well, I say we've learned before, you may or may not realize that a square root has actually a positive answer and a negative answer. We'll hit that later at about this time next year, actually, pretty heavily in algebra 2. But so that's why it says the positive root. But don't let that stress you. Don't let that throw it off. This right here is really the gold in this. So we have kind of a example with this is kind of a simple example, not a worked example. We'll do that in next thing. The geometric mean of a equals 9 and b equals 4 is 6 because the square root of 9 times 4 is 6, because 9 times 4 is 36. Square root of 36 is 6. Let's actually work an example together, finding the geometric mean. So we're going to find the geometric mean between 8 and 10. So it's going to be the square root of 8 times 10. Now, I'm going to kind of start in this lesson teaching us something that you may have learned some in algebra 1, possibly not. I don't know what your background is, but we're going to reduce this radical but keep it exact, right? And I'm going to do it two different ways on this one. Kind of the more typical way, which will be over here, and then kind of a way to think through this particular example even easier. So typically when we reduce a radical, we have this. So 8 times 10 is 80. So the square root of 80. So when we're reducing a radical, we're looking for a perfect square that goes into this number. So what are perfect squares? Remember, so perfect squares. We're kind of getting a 2-for-1 lesson here, basically, is what we're doing. We're kind of getting some preview for next year and some more early practice. And at this point in the spring semester, this is a great idea. So what are perfect squares? Well, perfect squares are when you multiply two numbers or a number times itself, you get a perfect square. So 2 times 2 is 4, 3 times 3 is 9, and 4 times 4 is 16. So then it would be 25, 36, 49, because 7 times 7 is 49. And then 64, and then 81, and then 100. We keep going, 121, 144, et cetera, et cetera, et cetera. There are an infinite number of these, right? They just the number squares. So are there any perfect squares that go into 80? Well, there are multiple that go into 80, right? So 4 goes into 80, and if we're not greatly mistaken, 16 does as well. But I'm going to pretend like all we see is 4 goes into 80. So we can split this root into, there's another theorem, actually, that you may have learned in Algebra 1, definitely will cover a lot in Algebra 2, that says if we have the square root of a times b, that equals the square root of a times the square root of b. So we can split that up, that multiplication up into two things. So that in relation to this, we can split this square root of 80 into the square root of 4 times what is 80? 4 times 20 is 80, right? What is the square root of 4? Well, the square root of 4 is 2, so we can do this as 2 times the square root of 20. Now, we want to make sure this is reduced all the way. Are there any other perfect squares that go into 20? Well, 4 also goes, which alludes to, I just said a few minutes ago, 16 also does. This kind of proves that because 4 times 5 is 20, right? So, and then 4 times 4 is 16. So we can split this into the square root of 4 times the square root of 5. Now, where did that 2 come from? That's just this one coming straight down. Square root of 4 again is 2. So we can reduce this square root of 80 into 4 times the square root of 5. Now, I will note that we could figure out how to reduce this particular example another way, and that's by factoring, see if there's a factor in 8 and 10. We can factor 8 into 2 times 4, right? 2 times 4 times, we can factor 10 into 2 times 5. Now, why would we do that? How would we know to do that? Well, if we have a common factor between the two numbers that we're finding the geometric mean of, that's going to be nice because that's going to make us a perfect square because 2 times 2 is 4. Now, this particular example is kind of crazy because we end up with 2 times 2 is 4. But then we also, 4 times 4 is 16. So we can split this up into 16 times 5, the square root of, using this theorem, we can simplify this into the square root of 16 times 5, 4 times the square root of 5. So the moral of the story is, in a lot of your homework examples, if you can find if these have a common factor, just factoring that out, and then you can split this into something that's reduced. Now, of course, obviously, we could get our calculator out and get a decimal approximation, which we may want to do if this was like a word problem or physics problem or something like that. So just to remind you, we can do that as well on these problems. So let's look at the next thing. So these are some pretty cool theorems. This is going to kind of lead to some things that are kind of awesome. If an altitude is drawn to the hypotenuse of a right triangle. So remember, an altitude goes from a vertex and then it is perpendicular to the opposite side. So we draw an altitude to the hypotenuse. The hypotenuse of a right triangle is that longest side. It's the side that is across from that 90-degree angle, right? Then the two triangles formed are similar. So this triangle is similar to this triangle, and they're similar to the big one. So in this particular example, triangle ABC, this big one is similar to triangle ACD, is also similar to triangle CBD. So all of those triangles are similar to each other, which is really, really handy. And this is kind of the foundation. This slide right here is where trigonometry is built on. This builds into all of right triangle trigonometry. Not all. Now, unit circle, which you'll learn later probably, not in this class, but unit circle comes at it from a different direction. But for just right triangle trigonometry, this builds everything else. So let's see a few things that it builds and starts to build. So if we have that same triangle, we're kind of illustrating some proportional relationships. So what we've got out here is this triangle with a altitude drawn from the right angle to the hypotenuse. And so that's the same as the one we had last slide. And then we kind of broke out all three triangles so it's easier to see, right? So this is the big one, this is this one, this is this one, right? And we've also written out all of the proportional relationships. So if we do a shorter leg to longer leg, shorter leg to longer leg, B to A equals H to Y equals X to H. So just short leg to long leg is this top row here. Now what I've highlighted on here is that you can see that when we write these out this way, you can see that some geometric means are formed, right? Because like right here, H and H are the geometric mean between Y and X. And B are the geometric means between C and X. And A are the geometric means between C and Y. So this idea right here leads us to the next two theorems that we're going to talk about. So let's write those down. Geometric mean with the altitudes theorem says the altitude drawn to the hypotenuse of a right triangle separates the hypotenuse into two segments. So we've labeled those in our little example as segment X and segment Y. The length of the altitude, so that H, altitude, CD, right, is the geometric mean of the lengths of these two segments. So it is the geometric mean between these two segments. So we can write this proportion or we can write it in this format. So we can solve for that altitude by finding the square root of the two segments times each other. And then also we can use the geometric mean leg theorem to set up two other different types of proportions. So the altitude drawn to the hypotenuse of the right triangle, same words, same, separates the hypotenuse into different segments. We've labeled them as X and Y in this kind of example. The length of a leg of the triangle, so like B is a leg or A is a leg, is the geometric mean between the length of the hypotenuse, so we've labeled that as C, and the segment of the hypotenuse adjacent to that leg. So B is the geometric mean between C and X. A is the geometric mean between C and Y, right? And so we've got that written. Let's do an example using this or these theorems, and then we're going to be through with this lesson. This lesson took a lot more time to prep than it does to present to you. Probably takes a little longer for y'all because there's a lot of pausing and writing, a lot of words. Sorry for that, can't be helped. That's sometimes the way things go. All right, so we've got this example. And this example I think is really cool, right? And let me tell you why I think it's really cool. So we've got this right triangle, and you might imagine that this right triangle was like the edge of a river or something or whatever else. And if we know the length of this and we know the direction we're headed, so like we're perpendicular here and we're pointing down the way to a specific point, then we can find all three of these lengths only knowing this one side, if this is a right triangle, because of the geometric mean leg theorem. That's super cool, right? Because the leg is the geometric mean between the hypotenuse and the segment on its side. So in this particular problem, Z is the geometric mean between 20 and I'll go ahead and write it all the way out. You're like, it's 25. Yeah, sure. But I'm going to go ahead and write it as 20 plus 5, right? Because it's this whole length, right? So now we just need to solve this problem. So Z equals 20 times 25, which is 500, Now we're gonna do this. We're gonna simplify it into an exact answer, and then we're also going to get our decimal equivalent on this one as well. So are there any perfect squares that go into 500? Well, yes, there are, because 100 is a perfect square, right? So we can simplify this into 100 times 5. Square root of 100 is 10. So this is 10 times the square root of 5, which is approximately equal to, now we're going to pull out our calculator. So we're going to take and do 10 times the square root of 5, or you could just put square root of 500. You'll get the same answer either way. So it is approximately equal to 22.3 units. Great. So let's find the other ones. Now, y we can find the same way, right? Because y is the geometric mean between 25 and 5. So y equals the square root of 5 times 25. 5 times 25 is 125. Are there any perfect squares that go into 125? Well, 25 does. We could have just left it right there in our simplification, right? So we can split this into the square root of 25 times the square root of 5. Kind of going back in time. So this equals square root of 25 is 5. Whoops. Times 5, which is approximately equal to the square root of 125, or 11.2. 0.2 units. Now, x is different, right? Because as we've got the specific altitude, right? So we've got to use our other theorem. So what is the other theorem, right? It says that the altitude is the geometric mean between the segments it splits. So x is the geometric mean between this 20 segment and this 5 segment. So x equals the square root of 5 times 20. So 5 times 20 is 120, right? So this equals the square root of 120. Are there any perfect squares that go into 120? Well, 4 does, for sure, right? 4 times 30. 4 times 30 goes into 120. So let's do that, right? Square root of 4 times the square root of 30. Are there any perfect squares that go into 30? Well, 4 doesn't go in, 9 doesn't go, 16 doesn't go. So no, that's actually, so this one is kind of a more ugly one. 2 times the square root of 30, which is approximately equal to, let's see, square root of 120 equals 11.0, right? Because it's going to push it up there, 11.0 units. And that is it for that lesson. It's a lot of things. There are really those theorems that we have in here for solving math problems. That's the most useful things as far as actually using it for homework, using stuff in this lesson for homework or quizzes or tests or those kind of things. Those theorems and how those things work, and the way the geometric means connect with those right angles. That's the most important bit for just practical use. The other and what things are is building to something else that's going to be really cool and useful. We'll see you in the next one. Do your homework, all those things. Have a great day. Bye-bye.